If this is your first time here, this isn't a standalone video. It's one chapter in a complete story, the entire history of evolution, from the first replicating molecules to you. Every organism we mention is your direct ancestor, not a cousin species, not something similar, your actual lineage, an unbroken chain connecting you to the origin of life. That's what makes this different from every other evolution content out there. Most of it is scattered fragments, dinosaurs here, early humans there, the Cambrian explosion somewhere else, all disconnected. But they're not disconnected. They're all chapters in the same story, your story, and you can't understand any link without seeing what came before it. Lungs don't make sense without swim bladders. Mammals don't make sense without reptiles. Each chapter builds on the last, and nothing appears out of nowhere. 4 billion years of your deep history told as one continuous thread. If that sounds interesting, Chapter 1 is in the top right corner. I'd recommend starting there. If you've been watching from the beginning, you already know what this is. Let's keep going. Our lineage now consists of fully terrestrial tetrapods living in Carboniferous swamp forests around 320 million years ago. These animals walk on strong limbs, breathe air efficiently, and have skin resistant to water loss. They hunt the enormous insects thriving in oxygen-rich forests, dragonflies with 70-centimeter wingspans, millipedes a meter long. But one critical constraint remains. They must return to water to lay their eggs. Their eggs are like fish eggs, small, jelly-coated, and permeable. On land, they dry out within minutes. This ties reproduction to ponds and streams, limiting where these animals can live and making them vulnerable during breeding. The innovation that breaks this constraint, the amniotic egg, opens the vast continental interior to vertebrate colonization for the first time. The amniotic egg is essentially a portable aquarium. The embryo develops inside a fluid-filled sac called the amnion, floating in its own private water environment regardless of external conditions. A second membrane, the allantois, spreads beneath the shell and serves as both a respiratory surface, with blood vessels bringing embryonic blood close to the porous shell where oxygen enters and carbon dioxide exits, and a waste storage bag where toxic nitrogen compounds accumulate safely until hatching. The yolk sac provides all nutrients needed for complete development. The shell itself is porous enough for gas exchange, but structured to minimize water loss. This system solves 3 problems simultaneously: desiccation, respiration, and waste disposal. The embryo develops from single cell to hatching entirely within the egg, never requiring external water. The first amniotes could reproduce anywhere, in dry uplands, deep forests, seasonal environments where water existed only part of the year, continental interiors, previously inaccessible, suddenly opened to colonization. By 312 million years ago, amniotes had split into 2 major lineages, distinguished by skull openings behind the eye. One lineage, sauropsids, gave rise to all modern reptiles and birds, lizards, snakes, turtles, crocodilians, dinosaurs, and their descendants. The other lineage, synapsids, is ours. Synapsids developed a single opening, low on each side of the skull, positioned to accommodate increasingly powerful jaw muscles. This seemingly minor detail marks a real evolutionary split confirmed by hundreds of other anatomical features. Early synapsids, called pyracolosaurs, dominated Carboniferous and early Permian ecosystems. Some remained small and lizard-like. Others grew to several meters in length. The most famous are sailed-back forms like Dimetrodon, often mistaken for a dinosaur, but actually more closely related to humans than to any reptile. Dimetrodon lived 280 to 270 million years ago and was an apex predator up to 4 meters long, and had differentiated teeth, large canines for piercing and smaller teeth for cutting. This dental specialization foreshadowed the complex tooth patterns that would later characterize mammals. During the Permian periods, synapsids dominated terrestrial ecosystems worldwide. A more advanced group, called therapsids, emerged around 275 million years ago and became the most successful land animals. Therapsids showed clear movement towards mammalian characteristics. Their teeth were highly differentiated: incisors for cutting, canines for stabbing, complex cheek teeth for chewing. Their limbs moved more distinctly beneath their body rather than sprawling to the sides, improving locomotion efficiently. Some developed secondary palates, bony shelves separating mouth from nasal passages, allowing simultaneous breathing and chewing. This reflects increased metabolic demands. An animal that needs constant oxygen intake benefits from being able to breathe while processing food. Then catastrophe struck. At 252 million years ago, the largest mass extinction in Earth's history occurred. Massive volcanic eruptions in Siberia triggered rapid global warming, oceans acidification, oxygen depletion, and ecosystem collapse. 90% of marine species and 70% of terrestrial vertebrates went extinct. The diverse therapsids that had dominated the Permian were nearly wiped out. Our lineage survived as cynodonts, small therapsids, mostly under 50 centimeters long, with advanced features including even more specialized teeth, upright limb posture, and likely elevated metabolic rates. While archosaurs, the group leading to dinosaurs, rapidly diversified and came to dominate Jurassic ecosystems, cynodonts remained small and unobtrusive, but they were accumulating features that would define mammals. The cynodont jaw underwent critical restructuring. In earlier vertebrates, the lower jaw consisted of multiple bones. Cynodonts had one large tooth-bearing bone, the dentary, that expanded backwards, becoming larger and more robust, while other jaw bones shrank. This allowed more precise chewing control. As the dentary took over jaw function, the small bones at the back of the jaw, no longer needed for jaw mechanics, eventually detached entirely and migrated into the middle ear, becoming the malleus and incus. Combined with the staples, evolved earlier from a gill arch, these three bones conducted sound from the eardrum to the inner ear with far greater sensitivity than the single-bone reptilian ear. This transition happened gradually through numerous species over millions of years, with some fossils showing intermediate stages where bones serve dual roles in both jaw and ear. Teeth became increasingly complex, with multiple cusps arranged in precise patterns, creating surfaces that could crush, shear, and grind simultaneously. Different cynodont lineages evolved different cusp patterns for different diets, insects, plants, or mixed omnivorous foods. Precise tooth occultation, bringing upper and lower teeth together in exact alignment, required sophisticated jaw control and neural processing. Evidence for fur appears in late cynodonts. Some fossils show tiny pits in snout bones where whiskers attached. Whiskers are specialized hairs, indicating hair existed elsewhere. Some fossils show turbinal bones, delicate scrolled structures in the nasal cavities supporting membranes that warm and humidify inhaled air. Turbinals are necessary in animals with high breathing rates to prevent water loss through exhalation. Their presence suggested high metabolic rates requiring insulation, or fur, to maintain body temperature. Fur only benefits animals producing substantial internal heat. The evolution of fur implies a transition towards endothermy, internal temperature regulation. Endothermy is metabolically expensive, requiring much more food, but provides enormous advantages. Activity, regardless of external temperature, sustained high-speed movement, and the ability to inhibit cooler climates or be active at night when cold-blooded animals are sluggish. Lactation likely evolved during this period as well, though mammary glands don't fossilize. The logic is straightforward. Endothermic metabolism is energetically expensive, and newborns face severe challenges. They're tiny, lose heat rapidly, and can't find food independently. Providing nutrient-rich secretions dramatically improves newborn survival. The precursors probably existed as glandular secretions moistening eggs, similar to fluids keeping amphibian eggs moist. Over time, these secretions became more nutritious and essential, eventually becoming true milk. By 210 million years ago, in the late Jurassic, one small-bodied cynodont lineage showed the most advanced features: precise dental occulation, complete secondary palates, large brain case indicating expanded brains, small body size suggesting high metabolic rates, and skeletal features indicating agile, possibly nocturnal lifestyles. These mammalia life forms lived in forest undergrowth, possibly eating insects and small prey, active primarily at night when they faced less competition from dinosaurs. Nocturnality drove evolution of enhanced hearing and smell, both characteristic mammalian traits. By 200 million years ago, in the latest Jurassic and earliest Jurassic, true mammals existed. They possessed fur, lactation, endothermy, 3 middle ear bones, precise dental articulation with complete tooth patterns, single-boned lower jaw articulating directly with the skull, large brains, and 4-chambered hearts. These early mammals remained small. Most were shrew or mouse-sized, and nocturnal, avoiding the dinosaurs dominating Mesozoic ecosystems. Mammals diversified into 3 major groups: monotremes, which retained egg-laying, marsupials, which evolved live birth with immature young completing development in pouches, and placentals, which evolved sophisticated placentas allowing longer internal development and more mature offspring. Our lineage belongs to the placentals. Through 150 million years of the Mesozoic, the age of dinosaurs, our ancestors remained small, mostly nocturnal mammals, evolving acute senses, sophisticated brains, and complex behaviors, waiting in the ecological margins for an opportunity that would come only when an asteroid removed the dinosaurs 66 million years ago.